Welcome, students. We've been taking a bit of time to look at polynomial functions, and now we're going to look at rational functions, which are very much related to polynomial functions. So a rational function is a function in the form r of x equals p of x over q of x, where p and q are both polynomial functions. So p and q are both polynomials. It's called a rational function because it is a ratio, and specifically a ratio of two polynomials. So as an example of a rational function, we might have f of x equals x plus 2 over x squared plus 2x minus 3. Now, although rational functions are constructed from polynomials, their graphs can end up looking quite different, and the biggest difference comes from the fact that the domains are not necessarily all real numbers. Here we have variables in the denominator, and we know that if the denominator is equal to 0, the function is undefined, and this causes a big difference between the graph of a rational function and the graph of a polynomial function. Now, we've already seen the graph of one rational function. Let's recall the function f of x equals 1 over x. It's not the most exciting rational function. The polynomial in the top is just a constant, and in the bottom it's just x. But this is a rational function, and by looking at its graph, we can see the element that we'll have for the graph of a rational function that we don't have for a polynomial. So here we have a sketch of the graph of f of x equals 1 over x. And the element that this graph has that a polynomial doesn't is an asymptote. Remember, an asymptote is a line that a graph is getting closer and closer to, but not touching, usually. I'm actually going to change that definition a little bit later, because we will see with a horizontal asymptote, it's possible that the graph touches it or even crosses it. But in general, at least for this moment, I want you to think of an asymptote as a line that a graph is getting closer and closer to. And we can have vertical asymptotes, we can have horizontal asymptotes, we can even have slant or diagonal asymptotes. But right now, I just want to look at this graph. There are two asymptotes. We have the vertical asymptote given by the y-axis. The graph gets closer and closer to it without touching on the right and also on the left, but on the left it's going down. And we have a horizontal asymptote. As this graph goes further and further and further to the right, it's getting closer and closer to the x-axis, but never touching it. And the same thing happens on the left-hand side, except underneath. So the difference between the graph of a rational function and the graph of a polynomial function is that a rational function is likely to have at least one asymptote. They do have a lot in similarity, though. They will always be smooth curves. So whether it's a polynomial function or a rational function, we're never going to have a corner or a cusp in our graph. They're always going to end up being nice, smooth curves. The only difference is we might have asymptotes here. Now, this is a graph that we've seen before on multiple occasions, but what about the graph of the example function over here? X plus 2 over x squared plus 2x minus 3. Because it's a rational function, it's likely to have asymptotes, just because I told you that graphs of rational functions will usually have asymptotes. But the question is, where will the asymptotes be? And Also, how do we look at the behavior near the asymptotes? Because, for example, here the y-axis is an asymptote, but on one side we're going up, and on the other side we're going down. So the first question is, where will a vertical asymptote occur We'll focus on other types of asymptotes in future lessons. And then the second question we have is, how will the graph behave near 1? And we're going to answer both of these questions. The first one is much simpler than the other. The first one, where will a vertical asymptote occur? Well, if we look at f of x equals 1 over x, the reason we have a vertical asymptote at x equals 0 is because the function is undefined when x equals 0, because the denominator is equal to 0 when x equals 0. So in other examples or other cases, we will generally have a vertical asymptote when the denominator is equal to 0, because at that point we know that the function is undefined. So these occur when the denominator is equal to 0. So then once we've identified a vertical asymptote, how do we figure out how the graph will behave near it, whether it's going up or down? And there's lots of different ways that this could work. There are vertical asymptotes that are going up in each direction, that are going down in each direction, that go down and then up, or up and then down. So how do we figure out what the graph is going to look like? Well, the answer is actually how we figured out this original graph. A couple of weeks ago, several weeks ago, I think at this point, when we graphed f of x equals 1 over x for the first time, we made a table of values and we looked at x equals 1 and x equals 1/2 and x equals 1/5 and x equals 1/10. We need to look at x values near the x value of the asymptote to figure out what's happening to the function values. Are they going up, 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 up and getting closer to positive infinity? Or are they going down, 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 down and getting closer to negative infinity? And we have to check on both sides of the asymptote because the behavior can be different on both sides. So we need to make a table of values near the asymptote on both sides. And that's exactly what we're going to do in the next video. We're going to go through this example to find out where the vertical asymptotes are and also what's happening to the graph near them.